Alright, let's have a quick look at resonance in an LCR circuit. Now, what we've got is the usual diagram where we've got a VL, voltage across the inductor, and we've got a VC across the inductor. Now this time, I've made them equal lengths. Don't know if they look equal, but they are equal. I've measured them. Now what happens when that happens? How does that happen in the first place? Well, it happens when our reactance across the inductor, which is equal to 2 pi FL, is equal to the reactance across the capacitor, which is equal to 1 over 2 pi FC. And when they are equal, our impedance equation becomes XC minus XL squared, which is 0, plus R squared. So it just means that Z equals R. So our impedance, or our resistance for the whole circuit, is just the resistance. This is the lowest resistance we can get, because if there's any number in these guys, it's going to be higher. So this is the maximum current situation. Right? Maximum current situation. And we call this resonance. Now, when you've got your V, your Z value, okay, Vs over Z equals I, or I times Z equals Vs. So Z is at its minimum, I is at its maximum, because Vs doesn't change. Also, when these cancel out, Vs will be parallel with VR, which is here. So our VR is that, and our VS is that, and they are actually the same value, and VS equals VR. So this is called resonance, and to get that we need these two guys to be equal. 2 pi FL must be equal to 1 over 2 pi FC. So if we bring the F's up on that side, F squared must be equal to 1 over 2 times 2, 4 pi squared times LC. So F, resonance, we'll just call it F a little more, must equal 1 over 2 pi square root of CL, or LC. And that's our resonance formula. And hopefully you understand it now.